All right, so today we're going to be talking about power. Absolute power. Or, okay, maybe not quite that exciting. But yeah, so we're going to start talking about this idea called power. Um, Really, what we're looking at is so velocity was how much distance you covered in a certain amount of time, and acceleration was how your velocity changed in a certain amount of time. Really, power is just kind of like those. It's just how much work or energy is being done in a certain amount of time. Um, for those of you that are really into cars, tractors, trucks, motors, engines, stuff like that, you know power typically is measured in horsepower when we're talking about those kinds of things. Uh, in science, though, the unit for power is watts. Um, or we could look at it as since work and energy are both joules, they're joules per second. And then we could go even farther, and we know that joules are kilograms, meter squared per second squared per second. So really, they're kilogram meter squared per second cubed. I would say this definition here isn't all that useful, but joules per second or watts, that makes perfect sense. All right, so don't get this watt confused with this work here. This is a unit. This is a variable. All right, so anyway, so back to what we're talking about. So power is how much work is done each second. It lets you know kind of how fast an engine can go. The more work you do in a second, hey, my phone, the more power you have. That doesn't mean that a less powerful engine can't do the same amount of work. It just means it's going to take more time. All right, so I think the best way to go about this one is to kind of just jump into the practice problem I have there at the bottom. All right, so I have a 193 kilogram curtain. And let's even do this the formalized way where I'm just going to list out what we have. All right, so I know kilograms is a measure of mass, so mass is 193 kilograms. And it needs to be raised 7.5 meters. So I could call that distance or x or anything like that. Let's stick with distance here. So we've got a distance of 7.5 meters. So the curtain needs to be raised that distance at constant speed in as close to 5 seconds as possible. So we have a time of 5 seconds. The power ratings for 3 motors are listed as 1 kilowatt, 3.5 kilowatts, and 5.5 kilowatts. All right, so kilowatts are just 1,000 watts, okay? Which motor is best for the job? All right, I'm not even going to care what the 3 motors we have are. I'm just going to try to figure out what power of engine do I need to lift this curtain this far in this amount of time. So, you may be asking Mr. E, we don't have work. Well, you're right, we don't have work. But what do I need to find work? You know, we have this equation we talked about a while ago that work was force times distance. The cosine theta part we're not going to care about here. To which you're still going to say, well, Mr. E, we have distance, but we don't have force. You're right. But I do have a mass, and if I'm raising a curtain, I'm lifting it straight up, that means I just need to find the force of gravity. Because that's the amount of force I need to exert to raise this thing up. So, let's go through. So we can now either substitute this in here. So like we could do power is equal to force times distance over time. And the force of gravity we know is mass times acceleration of gravity times distance over time. We could do that. That's easy enough to do. In fact, I just have it solved there. But let's just start by finding the force of gravity, which is just mass times acceleration due to gravity. So we've got 193 kilograms times 9.81 meters per second squared. I'm not going to care about the signs for this part, just because they're not really going to affect my answer. So 193 times 9.81. 1,893 is where I'm going to leave it. All right. 1,893. That's force, so that's newtons. All right. So now I can find the work that we did to go against gravity is force times distance here. So 1,893 newtons. The distance I'm raising it is 7.5 meters. Bring this back over. Times 7.5. Let's call that 14,200. So we've got 14,200. Work is the type of energy. It's in joules. All right, the transfer of energy, I should say. All right. So now I figured out the work. So now I can come through and I can figure out that power is equal to work divided by time. So I've got the 14,200 divided by the time we said was 5 seconds. Bring this back over. Oh, there we go. Divided by 5. So I need 2,840 watts. 2,840 watts, or if I'm converting this into kilowatts, we just move the decimal 1, 2, 3, or 2.8 kilowatts. All right, so this thing's going to take 2.8 kilowatts of power in order to lift up. So out of my choices of 1, 3.5, 5.5, I don't want to pay for more motor than I need. So that 3.5 kilowatt is enough to get this job done in that 5-second amount of time. And here's to show like doing it the step-by-step way is the same. So here we had 193 kilograms times 9.81 meters per second squared times 7.5 meters all over 5 seconds equals, all right, so let's bring this back over. So 193 times 9.81 times 7.5 divided by 5. Same number we got before, so we're doing good. This right here, let's put a box around it so I know that's how much work I need. The correct answer is we would use or would need legible handwriting, the 3.5 kilowatt one. Okay, so that's really the answer we're looking for. But we would need the math to prove why. All right, so that's power. Energy works the same way, if we're transferring a certain amount of energy. Typically, when we start talking about watts and stuff, we want to go to light bulbs because they're listed in wattage, and that is how much electrical energy they use each second. And luckily now we have the LED ones, which use far less energy, so that just makes them better for our pocketbooks and for the environment. But that energy we're going to take a look at second semester. So with that, good luck with the practice problems.